Morning, guys. We are at it again. We're actually starting our new, our second part, I guess, say, to the acid base chapter. And this section is not as long as the previous chapter was, but I would say it's actually probably a little more abstract. There's a few different concepts that we're going to come across that are a bit more. Uh, yeah, just I guess abstract's the best word for it because it's definitely not as it's a bit mathematical, but the theory is a little stronger to get through. Um, but a lot of the sections we're going to cover in this chapter, these sort of all revolve around a central theme, which is good. Um, but just getting your sort of head around that concept can be tricky, sort of thing. So today's lesson shouldn't be too long. We're going to look at measuring the pH and POH of a strong acid mixed with a strong base. And this is fairly heavily calculator use, so make sure you have a calculator handy. And we'll have a Zoom meeting tomorrow, and hopefully be able to address some of your questions then. So I'm going to share the screen here with my OneNote, and just going to sort of pose a question to you here. And that is, if you were to mix something like hydrochloric acid with sodium hydroxide, and that's sort of all you were told, what do you think would happen if you did that? You just kind of poured these chemicals together, or various amounts of these chemicals together. What do you think would happen? Well, we know the pH of the HCl would have to be below 7, and the pH of the NaOH had to be above 7. And then I guess it would depend on the concentration of the chemicals that would govern what their numbers would be. And so what we're going to look at is how to determine the pH when we mix those things together. So let's say that the HCl was 0.10 molar, and the sodium hydroxide was also 0.10 molar. So they have the same initial concentrations, and you mix them together. But let's say you took 20 milliliters, 20.0 milliliters of the acid, and you were to mix it with 40 mils of the base. So although you had equal concentrations of chemical, you have different volumes being mixed together. So like you just to think about what the pH would be here for this. Okay, and let's give you a starting point just so you get a sense of what the initial pHs of these things would be. So the base, now because it's a strong base, NaOH is considered a strong base. It dissociates 100%. So you would get sodium ions, and you would get hydroxide ions, and the hydroxide ions would be 0.1 molar, and we could easily find the POH of that chemical, which would be the negative log of that number. And then to find the pH, we would do 14 minus the POH value. Now you could do this question without a calculator because we are working in base 10, but just get used to using the calculator again. Negative log of 0.1 gives us a POH of 1. So the pH would be 14 minus that number, which would be 13. So the pH of this would be 13, I guess with sig figs 0, 0. And then, of course, the pH, well, HCl is a strong acid. So strong acids, when they react with water, ionize 100%. So you would get 100% conversion to hydronium and chloride ions. And the concentration of the hydronium ion in this beaker would be 0.10 molar. So to find the pH, we would negative log that number, which gives us a pH equal to 1.00. So we have very acidic conditions and very basic conditions. You would not want to put your fingers into this stuff or drink it or something silly like that. But if you mix them together, do you think it would be safe to drink, or do you think it would be, a little bit more on the acid side or a little bit more on the base side? Well, you might conclude, if you sort of think back to chemistry 11, that if you were to mix hydrochloric acid with some sodium hydroxide, that actually would be a neutralization reaction. And so you might say, well, look, I would get water forming through neutralization, and I would get NaCl forming. And because they're both solutions, I know the water, of course, would be a liquid, but the sodium chloride would be in solution form because it's not a low solubility salt. So you'd have lots of sodium ions, lots of chloride ions. So would this just taste like salt water to you? Like, would you be able to drink that? Or do you think the pH wouldn't be 7? Because when we say neutralization, most people, I think, immediately jump to pH 7 when we say neutral. So would it be neutral or would it not be neutral? So that's what this lesson is all about, is trying to determine what would the actual new pH be. But I'd like you just to right now just take a guess. If you started with pH 1, pH 13, you mix the two things together, use 20 mils of one chemical, 40 of the other. Like you just in your head, or at least write down on your notes what you think the pH would be. Because I think sometimes in science, things seem like they should just be intuitive, but they're really not. Like they just don't seem to follow what your gut might actually tell you, or maybe your gut does tell you the right thing. So anyways, just take a stab, and I want you just in this little box right here, just think what the pH would be. Okay. So I just pulled this question up from my old notes and stuff like that. And last year when I asked a question similar to this year, I had numbers all over the place of students. I think sometimes students just guess numbers, but we'll see how close we are to your number here. Okay. So let's try this. Okay, so I'm going to take a look at, first of all, what I might want to find out are how many moles of hydronium do I actually have in this question here. And so if I was to find out moles of hydronium, this would be 0.10 moles per liter multiplied by 0.0200 liters, because that's what 20 mils would be. And that would give me, move the decimal one place, 0.00200 moles of hydronium. Now, sometimes in the book, you'll see this written, H+, and that's sort of okay in terms of the idea that there's proton ions here. But we know from our understanding of proton ions in water that they would all be converted to hydronium. Now I guess we could work out the moles of OH+, sorry, OH-, and that was the same molarity, so 0.100 moles per liter. But now we were using a volume of 0.0400 liters. And if we convert that, we move the decimal one place over, 0.00400 moles of OH minus hydroxide. So if we just look at the two numbers and think, well, we know that when an acid and a base react, really the H pluses and the OHs, let me pause this. Sorry guys, I was just reinsuring my truck actually. So here we go, back to the question. Okay, so we have H plus OH that should form into water. And of course, for every one of those, we'd use one of those. So if we had equal amounts of those ions, then we should have neutral pH 7 water. But we can see that we actually have more hydroxide. There's more hydroxide than there is hydronium. So that would indicate that we should have a basic solution. So I would think there would be more hydroxide, so the concentration of the hydroxides would be greater than the concentration of the hydronium. Therefore, the solution is basic. Now, when we say basic, do we mean like it's like 7.1 or maybe 7.2, maybe 8? Or, how close is it to that number we asked you to sort of take a stab at here? So what we could do is we could try to figure out what is the concentration of the hydroxide after we mix chemicals together. So if we kind of use this idea here that for every one proton or every one hydronium, we would react it with one hydroxide. We could find out the moles of hydroxide that are in excess here. So if we look at moles of hydroxide in excess, then we could say, well, let's find that out. So basically we have 0.00400 moles of OH, and we're reacting it with 0.00200 moles of H pluses or hydronium. So that should give us an excess, assuming they all react 1-to-1, that we would have an excess of 0.00200 moles of OH. So that would be the excess moles, but in order to find pH, we actually need to know the concentration of the hydroxide. So to find concentration of hydroxide, that's going to be equal to the number of moles in excess, how much we have left over, which is that number. And then we need to divide that by the volume. But now we have to remember that we mixed two different volumes here. We took 20 mils and we added it to 40 mils. So 0.020 liters plus 0.0400 liters. Or many of you would just say, why wouldn't you just say 0.06, which is really what it is. So really it's 0.00200 moles all over 0.0600 liters. And that gives us, let me work this out, 0.002 divided by 0.06 gives us a concentration of about 0.0333 blah, 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 molar hydroxide. Now, once again, this is the concentration of the hydroxide, so we can find the POH. So the POH would equal the negative log of the hydroxide, which is 0.0333, just repeating. And then that equals a certain number. And then the pH, let's do pH here, that would equal 14 minus the POH. So basically whatever that number is there. So you don't need to show that middle step, but I'll just write it out to show it. But negative, let's see, negative log of 0.0 and then like 333333333. And so that's giving me a POH of about 1.477 and a bunch of other numbers. And so if I do 14 minus that number, where's there? Sorry, negative log 0.033333, and then 14 minus that number, I'm getting a pH equal to 12.5, and I think it's 2 sig. Is it 2 sig figs? 3 sig figs. It's actually 2 sig figs because this actually was just, this should be 2 sig figs here. Because our concentrations are 2 sig figs here. So I think I should have not had so many, zeros here. Wasn't too worried about that because that's not our final number. So, but anyway, so it's 12.52. So how does that compare to what you thought? I remember when I first did this question, not really thinking about the numbers, I assumed it would be much closer to 7 than that. Because remember before, it was 13. And now it's 12.52. So basically you added half the volume with this of the same concentrated acid as you had base, and the pH barely moved. It went from 13.00 to 12.52. So you added a whole bunch of acid to this thing, and you barely budged the pH of the base. Like it really didn't do much damage to it. That might not be maybe as intuitive as you might think here in that. Okay, so now I'm going to do the same question. I'm going to do it a slightly different way, what I think is a faster way. And this actually is a method called the concentration method, just focusing purely on concentration. And I would encourage you to try this method. It's a little more abstract. It doesn't quite maybe ring as well as moles, but it's a lot less calculations. And I think for a lot of you guys, it'll just be much easier for you to do. So the concentration method kind of relies on you making a determination, and that is about whether it's pH or maybe a POH question. So probably would ask you one of those two things. And you're going to use one of two formulas. One of them would be the concentration of hydronium would be in excess. So I'm going to use the letters X and S for excess. See how clever that was? And that's going to equal to the concentration of the hydronium that you started with, so St, minus the concentration of the hydroxide you started with. And that's kind of related to, I'm just going to draw an arrow here, to this. When you're basically saying that the moles of one react with the moles of other, and you're going to have an excess amount. However, in the question we did above, it was actually the other way, in that the hydroxide turned out to be in excess. And so we're going to take the concentration of hydroxide we start with and minus the concentration of the hydronium we start with. So this kind of question involves basically you needing to determine, if you're going to use this method, which formula you're going to use here. And that actually is probably the trickier part of the question. But I don't think it's that tricky if you work it out. So let's work out the concentration. This is the question we just did here. And let's find the concentration of the hydronium. So we're going to find concentration of hydronium. Show me, I'll use red. It's always nice to color coordinate things. So let's use the color of the color. Let's use the hydronium concentration that we start with. Okay, and what I mean by that is the concentration of the hydronium after you've added it to the base, but before it has reacted. So it's really a dilution question. So I'm going to go back to the beginning here just to show you some numbers here. So the initial concentration of the acid was that, and since it's a strong acid, the hydronium also has to be that number, 0.1 molar. We said that up here. Okay, so that's the concentration of the hydronium, is 0.10 molar. But now what I'm going to do is look at it in terms of after you have diluted it. That means you've added it to the base. So we need to know the volume of the acid added and then the combined volume in the end. So we had 20 mils added to 40, which is 60 mils. Now the reason I prefer this method is I'm not even going to change the milliliters here. I'm just going to keep it as milliliters. So I'm going to say 20 milliliters over a total volume of 60 milliliters. I'm just going to draw a little note here. This is total volume, right? So that's once you've combined them. And this up here was the initial volume. So you might remember from grade 11 chemistry, this is referred to as a dilution calculation. So I'm going to say, well, let's work that out. 0.1, was it 0.0 or 0.1? 0.1, good. 0.1 multiplied by 2 divided by 6. So I get 0.0333333 molar, oh come on, really? Molar hydronium. And then I'm going to do the same thing for the hydroxides now. So hydroxide is sorry guys, pause this again. Okay, car insurance again. Okay, so we start with 0.10 molar. And now our dilution factor is 40 mils of base over top of 60 mils of combined volume. And so I work that out. It's going to be 0.1 times 4 divided by 6. And now I'm getting 0.066666 ... molar hydroxides. Okay, so you might remember at the very beginning I said you had to choose which formula to pick here. So you have to know which one's in excess. So if you do it this way, you just look at the two numbers, you think, well, there must be more hydroxide than hydronium. So I'm going to have to use the bottom formula here. So the concentration of the hydroxide that's in excess is going to be equal to the concentration of the hydroxide we start with minus the concentration of the hydronium we start with. Now, I actually do this as a column a math problem because you might remember when you round with sig figs, when you're adding and subtracting, it's different than when you multiply and divide. So you might be you need to be very careful about how you do that. This question, it wouldn't actually make a difference for this specific question, but there's lots of questions where it actually will, and I'll try to hopefully create one that shows that. So I'm minusing 0.03333. And of course, you can just sort of eyeball that and say, well, that's 0.33333. Now, as far as let's go pH here. Well, I guess first of all, I would do POH. So that would be the negative log of that number, which is the same number we got above. And to do pH, we do 14 minus the POH. So we should be getting the same number we got above, 12.7052. So not even less than half a pH unit difference. Okay, so sig figs here, I guess, is the big question. So sig figs, this number here, it should have 2 sig figs, which means it's accurate to the third decimal place. This number should also have 2 sig figs, which means it's also accurate to third decimal place. So whenever we subtract these numbers, our number is only valid to the third decimal place. Not 3 sig figs, third decimal place. So that number has 2 sig figs in it. So our final answer has to have 2 sig figs in it, which it does, which is 12.52. So I just want to show you a question. Imagine initial concentration was 0.06, I don't know, say 0.0, and you minus let's say it was accurate to the third decimal place. Let's say it had 3 sig figs. It was accurate to here, okay? And then you subtracted 0.0591, something like that. And so if you do that, so you're saying, okay, well, 0.06 minus 0.0591, and I'm getting 0.0009. And of course, a bunch of zeros after this. But if you think about sig figs, this number would have had 3 sig figs. This number would have 3 sig figs. But when you get to the answer, your answer can only be accurate to the least precise measurement. So this first number is accurate to the 4th decimal. This is accurate to the 4th decimal. So your number can only be accurate to the 4th decimal, which means technically this number now has 1 sig fig in it. So if you're trying to find the pH or pOH of this, your answer can only have 1 sig fig. So I would really encourage you to do it as a column. If you just type it in your calculator, you're probably never going to see where you truncate the number to. So that can be quite tricky here. Okay, so let's try a different problem. And I'm going to use this new method of solving it. And let's say that you have a beaker that has lots of acid here. So let's say it's 0.020 molar HI, and you have 30 mils of that, and you're mixing it with, another beaker that has 0.10 molar KOH, and let's say this is let's say it's I don't know, let's say 10.0 milliliters. Okay, so we've got different concentrations and different amounts of chemical. And so it may not be very clear right now what is actually in excess here. So I would just solve for concentrations. I would just work out the two concentrations, say, well, the concentration of the hydronium is equal to an initial concentration of 0.020 molar. Now remember, the only reason we can do that is HI is strong. If this was HF, you wouldn't be able to do that. That's where you'd have to use an ice table here. But because it's a strong acid, you can just say it's 0.020 molar. And now we have a dilution factor. We're adding 30 mils of this to 10 mils, so we'd have 40 mils. And so if I work that out, 0.02 times 3 divided by 4 gives us 0.015 molar. So that's the concentration of the hydronium after the dilution. And the concentration of the hydroxide, its initial concentration is 0.10 molar. And now, so we start with, and where are we here? Oh yeah, so in our initial volume is 10 mils, divide by a total volume of 40 mils. So we go 0.1 multiplied by 1 divided by 4. And so we're getting 0.025 molar, okay? So which one's in excess? Well, although there's less volume, because the base is so much stronger than the acid, it's once again, it seems like the hydronium is in excess. I'm thinking the pH is going to be above 7, so hydroxide is above hydronium. So I would use the formula that the concentration of the hydroxide in excess should equal the concentration of the hydroxide we start with minus the concentration of the hydronium we start with. So that would be 0.025 molar, and then I'm minusing 0.015 molar. And I get, and once again, here's a question, I'm going to be kind of careful here. I get 0.01. But technically, how many sig figs should this number have? Well, this is 2 sig figs, this is 2 sig figs, but more importantly, this is accurate to the third decimal, therefore accurate to the third decimal. So we do have to put a third decimal. Now you might say, well, look, it has 2 sig figs like the other ones, but that's not the reason why. It's actually because the numbers are accurate to the second decimal. So if you're trying to find pH, let's just find pOH first. That would be the negative log of that number. How fortuitous, it turned out to be a base 10 number. So that should be 2.00. Negative log 0.01, I, Captain. And the pH here should be 14 minus that number, which is 12.00. So it's actually quite basic. It's quite a basic solution. And once again, you wouldn't want to be drinking that or tasting that at all. Not to mention there's different ions here. You've got iodide ions and potassium ions, and that might mess your nervous system up a bit. So besides giving you a wicked chemical burn, your stomach opening up and your guts dissolving and stuff. But, you know, it's kind of fun to try things. Anyway, so there we go. So there's a question. So our last question for the day, last question here is sort of a reverse Roux question. So let's see if we can do that. So let's say you had 50 mils, as an example here. Let's say you had 50 mils of 0.200 molar, let's do lithium hydroxide. Okay. And it produced a pH. So you add, sorry, this here, lithium hydroxide. How many? I should have phrased this question from the beginning. Sorry. How many moles of HCl is required to result in a pH equal to 11.300. Okay, question mark. Okay, so so we got this beaker, we've got lots of base in there. It's a strong base. So you've got some lithium hydroxide. So that should produce lots of lithium ions, but more importantly, lots of hydroxide ions. And we are adding a certain amount of acid, and we're curious about how many moles of the acid would we actually have to add to do this in the process. So once again, if you use the concentration method, you're going to have to determine which formula you're going to work with. So we have to determine, are we using the one where the hydronium is in excess? So are we using that one? Or are we using the one where the hydroxide is in excess? And you might remember from earlier videos when I talked about pH and pOH, a lot of students sometimes think that if they're being asked, what is the pH, what is the pH of something, that we're implying that it must be somehow acidic. But that doesn't need to be true. The pH is just a number here. So I'm going to take a look at what I know from the question. Well, I know initially that the concentration of hydroxide that I would start with would be equal to 0.200 molar. And then I'd have to multiply it by a dilution factor, okay? Now, when we add HCl to the compound, we could add it in the form of a gas. We weren't really told that, so I guess I probably should have said that. So we could bubble hydrogen chloride gas through the water, or through the base, and that would not alter the volume of the solution. So it's not like adding a solution of HCl, which would clearly change the volume. So in this case here, the concentration would stay the same. It would be that number right there. And if we actually knew the hydronium concentration that we started with, then we could actually just answer the question outright. So that's actually what we're going to have to figure out. We're going to figure out how much hydronium did we actually add to this thing. Because once we get that number, we can work backwards to find out the number of moles that was required. Okay, so what else do we need? Well, we need to know which one's in excess here, and that's the last bit of information we haven't used yet. That's this pH equals 11.300. So if someone said the pH was 11.30, do you think basic or do you think acidic? Well, I think basic situation. And so I know the concentration of the hydroxide would have to be in excess, and that its concentration would have to be the antilog of that number. So 10 to the negative 11.300. So I already know the formula I'm going to use is the concentration of hydroxide in excess must equal the concentration of hydroxide we start with minus the concentration of the hydronium we start with. And keep in mind, that's what we're actually trying to find out. That's the amount we want here. So I might rearrange my equation and work it out as the hydronium we started with would have to equal the concentration of hydroxide we started with minus the concentration of the hydroxide that was in excess. Just rearrange the equation. So this number here is 0.200, and then we're minusing the antilog of that. Actually, sorry, that is incorrect. Sorry, this here, this is what we want to find out, but actually, this here would be the concentration of the hydronium. So the concentration of hydroxide in excess, we could find out the pOH. I think that might have been a better way to go here. So the pOH would be 14 minus that number. So 14 minus 11.3 is 2.700. So the hydroxide concentration would be the antilog of the pOH, which is negative 2.700. So if I go 10 raised to the negative 2.7, I'm getting, and I'm going to write it in decimal format here, but there's 10 to the minus 3, so 0.01995 blah, blah, blah. So I'm going to go 0.2 minus that number, and I'm getting a number of 0.19800047 and a bunch of other numbers. Okay, so with sig figs, this number here would be accurate to the third decimal place. This number would be accurate to the 5th decimal place. So we can only be accurate to the least precise number, which is the third decimal place, which is this number here. So this number, whatever it turns out to be, is going to be 3 sig figs. So what we're being asked to find, we're being asked to find the moles of base, or moles of acid required here. So I know that the H3O plus in excess, so the concentration of the H3O plus that's in that was we started with, is 0.19800047 blah 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 moles per liter. Okay, so I'm trying to find the moles of the HCl required. So I'm going to start with that number first. So I'm going to say I need 0.19800047 moles per liter of hydronium. Okay. Now, because the acid is HCl, there would be one HCl per one hydronium. So basically, it would have all come from the HCl here. And then the volume that we're putting all this through is 50 milliliters. Now, here's where we're going to be careful. You might remember in the concentration, I was able to do dilution calculations by not changing the volume. But because this is in liters, I need to work in liters here. So this has to be 0.0500 liters. I cannot keep that in milliliters. I'll be up by a factor of 1,000 if I don't change that. So if I times this through, so I take my original number, it's 1-to-1, and then times it by the volume of 0.05, I get, now it should be 3 sig figs here. So 9.90 multiplied by 10 to the minus 3 moles of the acid HCl. If it asked for grams, then you would just times it by the molar mass, which I think is like 36.5 or something like that. Okay, so I hope that's is not too crazy, but the formulas are in the book there, so feel free to look that up. We do have a Zoom meeting tomorrow if you want to. And the questions for this are on page 143, number 50. I was thinking of the new section, but it's just a continuation of an amazing chapter, 58 to 67, say. Okay, they do take a little bit of work, but I don't think they're too tricky. But I would really encourage you to get through those before you start the next lesson. Okay, let me just stop that.